This flare is burning gas from a subsea well offshore Melville Island in the Canadian Arctic, in 60 meters of water, under 2 meters of ice. The gas is flowing ashore through the world's first Arctic marine pipeline, engineered by R.J. Brown and Associates, who were chosen to tackle the awesome task of designing and developing the special procedures and equipment needed. Our experience covers a decade of offshore engineering worldwide. The company can draw on a broad knowledge of advanced technology and finds innovative solutions which reduce construction costs and risks so that pipelines can be built in places previously thought impossible. When we take on a pipeline project, we can offer a complete engineering and project management capability, covering all aspects from initial survey and feasibility study through design engineering, procurement, inspection, and construction supervision, on to commissioning and operation. Major pipeline projects have been managed all over the world for many different clients in very varied environments. This film tells the story of Project 1448. The Canadian Arctic, one of the last frontiers for offshore exploration, the harshest environment yet faced by the oil industry. Pan-Arctic Oils drilled for hydrocarbons in the Arctic islands and found the huge Drake and Hecla gas fields. Drake, F-76 was chosen to demonstrate the new technology needed to bring into production offshore gas fields in up to 500 meters of water. RJBA starts the survey program in February 1977. The survey will take into account the many factors that can affect the well and the pipeline: ice movement, onshore topography, ocean bottom profile, permafrost, soils, and ice scour. The bottom is soft mud, free of boulders and rock, and permafrost occurs only very close to the shore. Side scan sonar, bathymetry, underwater television, and soil data are analyzed and plotted on site, and laboratory tests are carried out.
And the only way we're going to get the survey done...
The results are forwarded to the RJBA engineering offices, and work begins on the detailed design of the makeup system and the equipment to be used to connect the pipe to the wellhead. The flow lines are critically important. Knowledge acquired in this project will be used in the construction of large offshore gathering systems under the Arctic ice. There are 2 flow lines. One of them has conventional heat tracing and is insulated with polyurethane. The other has skin effect current tracing, SECT, a new method for offshore pipelines, but one that has great promise. Smaller lines are needed to control the well hydraulically from shore and to inject glycol into the gas to suppress hydrate formation. All 7 lines are bundled together inside an 18-inch casing, held on spacers, dry and secure against mechanical damage and corrosion. 300 meters of the shore zone crossing are encased within a 24-inch pipe used for the freezeback pipeline protection system. RJBA devises a new connection procedure. It is designed to be completely independent of divers or submersibles and uses a Reagan mechanical connector between the wellhead and a module at the seaward end of the pipeline. The whole procedure is simulated in detail on a model in our office. The concept is to pull the complete bundle from the shore with the seaward end at first offset 50 meters to one side of the wellhead. The first 300 meters of pipe floats just above the bottom, supported by buoys, but held to the correct height by drag chains. 2 cables flex the floating section sideways until the module is in front of a guide frame on the wellhead. Pump-up buoys then lift 2 more cables from the module to the surface. They are threaded through the guide frame and pull the module the last few meters until it can be locked in place. The connection module is manufactured in California. Here, a series of tests are carried out to check that the module connects correctly with the guide frame and that the connection method will accept small amounts of misalignment. During the test, the forces required to deflect the pipe and the strain set up are checked against theoretical predictions. The tests show that the connection module engages correctly with the guide frame and can be clamped in place by locking wedges. At the shore, the pipeline has to be protected against ice. It is to be pulled into a trench, plowed in the seabed, 1.5 meters deep and 3 meters wide. Plows have been used previously for making trenches to cross shallow rivers, but it was RJBA who perfected and used this technique successfully in deep waters in the North Sea. Because the bottom of the sea at Drake Point has been found to be extremely soft, a special design is required, large enough to keep the spoil from falling back into the trench, but still light enough not to sink down into the soft mud. A first design is made and a model test on a mud flat shows that the plow cuts a good trench. Skids at the front hold the plow to the correct depth, and mold boards move the spoil away. Using the results of the model tests, we design the full-scale plow, and it is fabricated in Calgary under our supervision. It is then tested in the Fraser River Delta, close to Vancouver, where bottom soil conditions are similar to those at Drake Point. During the summer, the site of the onshore facilities is being prepared. Materials and equipment arrive at Panarctic Oil's main base, Ray Point on Melville Island, during the annual sea lift, and are then transported by Hercules and Twin Otter aircraft to Drake. The weather is not always cooperative. In the Arctic, winter darkness is continuous. The temperature drops to -50, and the wind reaches 100 kilometers an hour. For the men working there, wind chill makes it as dangerous and uncomfortable as still air at -110 degrees. In November of 1977, preparations begin at the well site. Panarctic's skilled crews have been through this routine several times before, the only people in the world to have done it. They use the extreme Arctic cold to thicken the natural sea ice, working with the environment rather than against it. A sustained flooding program builds an ice platform 7 meters thick. A large heated tent is built close to the shoreline, and all the pipe welding and makeup are done undercover. a painstakingly thorough inspection program, every inch of every weld is scanned for the most minute defect. First, the casing is made up, section by section, and pulled landwards. Then the flow line bundle is welded together, installed on the spacers, and pulled into the casing by a winch, 1,200 meters inland. The pipe is later going to be pulled into the sea by an ice base winch out on the ice. A trencher cuts through sea ice 3 meters thick to make a continuous slot along the cable route, and then the pull cable is dropped through the slot onto the bottom. A rectangular hole is cut so that the plow can be lowered through the ice. Hydraulic ice tongs then remove giant ice blocks, each weighing up to 8 tons. Because the air is so cold, the water in the hole refreezes rapidly. Insulating boards are placed across it, and warm air is blown underneath to keep the hole clear of ice. The next stage of the installation is to plow the trench for the pipeline in shallow water. The plow is carried out hanging on a spreader beam between 2 trucks, one on either side of the hole, and then lowered to the seabed. The plow is then pulled from shore by the main pull winch, excavating a trench 300 meters long under the ice. A profiler survey of the trench confirms that it has been cut to the design depth of 1.5 meters. The pipe bundle is now complete, and the connection module is welded to the front end, inside the makeup tent. A check is made on the release system used to lift the 2 pull-in cables to the surface from the module. Buoys are installed on the first 300 meters of the flow line to lift it above the seabed. Each buoy carries a transponder, which will be used to pinpoint the exact position of the pipe as it is deflected sideways.
We got one,
in late March, preparations for the pull are almost complete.
One over here. Say that's the center line where we pull.
An RJBA engineer briefs the contractor's personnel on the pull procedure.
We position that winch here, the drums here, into 3 lines running down. Then we're going to do just like in the past. We'll cut 2 small holes, put a strobe light in here, and the diver will go ahead.
At the shore end of the pipe, a hold-back winch checks the forward movement.
Start it rolling now.
Tractors at the front end help move the pipe forward from the launchway. The connection module moves into its prepared hole in the ice, and it's followed by the flotation buoys. When the first 300 meters of pipe are in the water, trim chains are hung on the pontoons to make the pipe just buoyant. It will float above the seabed with the chains dragging on the bottom. The pipe is pulled by the main pull winch far out on the ice until the connection module is level with the wellhead guide frame and 50 meters away to the west.
Your eye on this one. That's getting up high.
It is time for the connection procedure to begin. The lateral pull winch begins to flex the end of the pipeline towards the wellhead.
Because they're taking that catenary out.
The whole operation is monitored from a control room, where all the information on cable movements, tensions, and wellhead positioning is brought together. As the connection module approaches the wellhead, frequent checks are made on its position. The computer-controlled transponder navigation system follows the movements of the bundle and continually transmits three-dimensional position information to the control room.
I can't stop till you stop.
Okay, hold her, Gary.
Okay. Okay, number 1.
Yeah.
9902.
6 meters from the wellhead, the module comes into view on the television screen. A dramatic moment, signaling the success of the lateral pull.
Number 2.
Now the connection module is in front of the wellhead. 2 more cables are released from the module, threaded through the guide frame at the surface, and then lowered to the bottom with the guide frame. These 2 cables pull the module into its final position. The television monitor on the wellhead makes it possible for the engineers in the control room to observe the connection procedure, inch by inch, and to check the movements of the connecting cones.
Come on. Oh.
As soon as the module is in place, wedges are lowered to lock it. The flow lines are pressurized to force plugs out of the ends. The module is then ready for the final connection between the wellhead and the flow lines by rams that push mechanical connectors from the wellhead.
Yeah, come in.
Make sure that they don't move that cable that we lower down and hook up to the SC.
Finally, the buoys are acoustically released from the pipeline. They float up onto the ice and are lifted up. In shallow water, the pipeline is subject to possible damage by floating ice during the breakup season in late summer. RJBA invented a new shore crossing system for this project. The flow line bundle is protected by a thick cylinder of artificial permafrost surrounding it. Another example of working with the Arctic environment. The permafrost is formed by circulating a refrigerant within the annular space between the main 18-inch casing and an outer 24-inch casing. Extra protection at the shoreline is given by an ice berm. The natural ice is artificially thickened by spraying water onto the surface and is then insulated against thawing by a layer of gravel on top. A gigantic step towards development of the enormous energy potential of the Arctic has been achieved. Ingenuity and technology have overcome challenges thought by some to be insurmountable. Among the new RJBA developments used in this first Arctic offshore pipeline were bundling the pipes in a casing, the end deflection system for accurately lining up the subsea connection, directed from a central control room, design of a diverless connection up to 500 meters depth, trenching under ice with the largest plow ever built, and protection of the shore crossing with artificial permafrost. We are proud to have been a part of this project, another successfully completed by RJBA through innovative engineering, planning, project management.